So we want to quickly look at log linear analysis. So log linear analysis is an extension of chi-square test. It will sound somehow. How can it be an extension of chi-square test? So at least we are starting from known. We all know chi-square, but to find the association among more than two categorical variables. You remember that chi-square is for association between two categorical variables. So in a situation where you have more than two, maybe you're having three at the same time, you cannot use chi-square straight away like that. So for you to do that, all of them, they are categorical. All the three or four, they are categorical. Is log linear analysis. So if you look at it, it's just try to borrow from regression, because if you remember, you only know the one we have treated before. Chi-square, they are bivariate, but is linear regression, you can say, can either be bivariate if it's simple regression, or multivariable. That is, when you have more than, in that case, you are having more than two variables involved in it. So in this case now, like chi-square, you have two categorical variables, you look at association. If you have three categorical, four categorical variables, and you want to look at the association at the same time, it's log linear analysis. And that is why it's somehow related to regression. And that's why even the logistic regression is a form of log linear analysis. Poisson regression, there are some aspects of it, there are a special type of it that will be is referred to as log linear analysis. So it is analogous to regression model, but all the variables, both independent and dependent, are measured on nominal scale. Have we seen that? On nominal scale, not even ordinal. Not so it's on nominal scale, they are categorical and nominal. All the variables involved, they are nominal. The technique is called log linear because it involves using logarithm of the observed frequency in constituency table. Log linear analysis may also be used to analyze multi-dimensional contingency table in situations in which no distinction exists between independent and dependent variable, and that is when the investigator simply want to examine the relationship among set of nominal variable measures. What would you mean by multi-dimensional? There are some, if you had a multi-dimensional scale, you just want to explore relationship between variable, plenty. In that case, you do, there's nothing like outcome or exposure. And that is what the principle that is being used in factor analysis also. Factor analysis, multi-dimensional scaling, just have a lot of variables. You want to see, are they related? So in some situation, if you have nominal variable plenty like that, you want to know, you just see, is there any association without yourself without you pinning down on some as of the outcome or exposure. So the fact that linear analysis does not require a distinction between independent and dependent variable point to a major difference between it and other regression models. And you see now, namely that the regression coefficients are not interpreted in log linear analysis. So when we say log linear now, it's related to regression model, but there's nothing like a regression coefficient interpreted in this one, because in all the regression, there's an outcome variable you are predicting in the regression. For linear regression, binomial regression, which logistic regression, even Poisson regression we are looking at, you have outcome variable, you have one or more exposure variable. In that case, you are trying to predict the outcome from the exposure. In that case, for each of the exposure, there must be a change in the outcome contributed by each exposure. In that case, each exposure will now have a regression coefficient that will tell you how much contribution they have made, each of them has made to the outcome variable. But in log linear, it's not like that. Nothing like that. Even though, so he's trying to borrow for regression, but it's not completely regression. So without wasting time, it's better to appreciate log linear by having an example, because you know, is because we are not talking of predicting anything from one another. It's just for you to look at association. Even though you know that in chi-square, doing chi-square, we are looking at association between categorical variable. Of course, you can as well say, okay, among these categorical variable, which one is outcome, which one is exposure. In log linear, you can have that also, but it's not limited to that. In log linear, you can even have where you don't even have outcome or exposure. You're just trying to explore, since it accommodates more than 2 variables. So can accommodate 3, 4. So it can accommodate as many variables as possible. In that case, that was why I now said that you can actually use it for in multi-dimensional contingency table, where you just want to explore association or relationship between different nominal variables. So let's quickly look at an example here. There's a contingency situation showing how many cat and dog will dance after being trained with different rewards. Here is, we have outcome variable here is actually dance, to dance or not dance. And the exposure variable here, to the type of animal, whether it is dog or cat. And apart from that, how do you train them? Do you train them with affection? When you pass, you just show affection, or you reward with food. You reward with affection to motivate the animal to dance, or with food. So I know that Professor Wakwe will find this one very interesting, because this example we are giving, it's more like psychological example, because the psychologists that train, we doctors don't train animal to do anything. So even if I don't think vet doctor train them, the psychologists that do that type of, and since the doctor that are closer to the psychologists, closer to the psychology are the psychiatrists, so they may be more interested in this type of research. Now, if you look at the first table, you will see that you see the animal, cat or dog. You now see that if they could dance or not, then reward, give food or affection. And you see, so if you look at it now, you will see total number of cats is 200, dog is 70, and how many cats could dance? 76. How many we don't dance? 124. Then how many cats food as a reward? Dance in response to food as reward? 38. How many dance in response to affection as reward? 162. So if you look at dog also, there are 70 of them. 49 dance, 21 did not dance. So 34 dance in response to food, while 36 dance in response to reward. So if you do this table I just put here now, many times if I give example like that, I first of all show the raw data, but it's difficult to show because we are talking of 270, so it's difficult here. It's not a small data set. So the best is to first of all summarize in a table, which actually is part of analysis on its own. Because even in a log linear analysis, you first of all run the analysis, do contingency table, first of all do cross tabulation to see the way it looks before you go into that log linear analysis straight away. So in trying to do that, if you remember in our regression, before you can use anything categorical variable for regression, you have to create dummy. So it's the same in even the linear analysis also, you have to create dummy. You cannot just put them, because for them to behave like as if you are running regression, you must create dummy. In that case, if you have two categories, you create one dummy for two, and all these cases there are two categories where the cat is either, the animal is either dog or cat. What you want them to be outcome is either dance or non-dance, and the other one is either affection, food, or affection, the motivator, what you motivate you to motivate. So in trying to code, look at this, the food for cat now. Remember, we say dance. You know, if you look at the table we put here, it's the same table, just try to create dummy. Training with for the training with dance and with affection. Okay, look at it now. We have for cat now, food, yes, no. Then affection, yes. Affection, no. If you look at, I don't know the best way to for us to understand this. Maybe it's better we open the data set. Let's open the data set. But before we open the data set, to look at, so that you can appreciate the way I created it done, because this is one of the things Dr. Kobo usually emphasize. So I prefer the practical. Let him be practical, because anybody can even present, if anybody get dislike and present this, but at the end of the day, how do we practicalize? How do we do it? And that is most important as far as I'm concerned when it comes to workshop. But before we go and look at the way we created the dummy, so I think it's better appreciated on the space where we created it, and something you can do. Now, let's look at what you expect. That will be, because you are having three variables here: animal, either cat or dog; training, either with affection or with food; and dance, yes or no, either dance or not. So each of them, since you are having more than one variable now, you know, if it is two variable, of course, we're just looking at association between two variables. How many times can you pair two things? Is once. So this one take me to what we have done before, during ANOVA, what we have done before during what do I call it? McNeema-Barker chi-square. So I want to ask, because it's a workshop, to be sure that you are following. I don't want to, because I want everybody to get it from this card. So how many times can you pair three things now? Because there are three variables here. How many times can you, how many ways can you pair two variables? And how many ways can you pair three variables?
Compare two variables in two ways. You can pair three variables in three ways. 1, 2, 3.
Two variables, only once.
2, 3. Sorry, once, I mean.
Two variables in one way.
One way, then three variables in
two ways.
Yeah, that's good.
Then three
ways.
variables
Three variables
in three ways.
Yes. So is there anybody having issue with that? If somebody is shouting?
No.
Okay, yeah, somebody said I do not get it.
Please, yes, so I had.
Okay, I'm coming. When somebody shouted, I do not get it when you say no distinction between independent and dependent variable. What does that no distinction mean? Okay. Then another one, please. What is the difference between this and the 3x4 chi-square table we often use? 3x4. What do you mean by 3x4? Okay. Okay, I understand what you mean now. So let me answer the first question. I think what I said in that one is very plain. the first question somebody had. When we say no distinction, that is, when you are doing analysis, there's nothing like, it's just like when you are running correlation. Correlation, there's no outcome, there's no exposure. I don't know if you know that. That's the logic behind correlation. That's what we are saying here. You know, when we are doing regression, we know that there's a variable that is the dependent variable, which is the outcome.
Dependent.
Yeah, dependent variable, which is the outcome variable. We also have one or more. If it is simple regression, one variable that is the independent. Or if there is multiple, more than 1, 2, 3, 4, 5, as many as possible, that the independent variable or the factors or the determinants or the exposures. So that in log linear, when we say we are talking, there are some situations you are just doing analysis, you are just doing exploration, especially if you are doing explorative factor analysis. Those variables, there are plenty. You just want to look at the relationship between them. You are not saying if one is outcome or the exposure. It's the same thing in correlation. Correlation is not looking at whether one lead to the other. They just want to, is there any linear association? So that's what we mean by there's no distinction as per dependent and independent. In some situation, we are not saying all. In log linear, in this case now, we know that in this scenario we have been provided, the outcome variable is dance. Is dance. So the exposure now, you can say there are two things that are exposure to the dance, the animal and the type of affection training method.
Training.
Do you train with affection or train with food? So do they dance in response to affection or dance in response to food? So here we can have outcome. Even if you look at it also, you can see that affection also, it depends on the type of the animal. So if you are trying to say, okay, for animal now, you can say both affection, the type of training rather, and whether they dance or not, is outcome to the type of animal. Can you see now? But if you have to look at the gradient now, the type of animal will determine the type of training they respond to. It's not the training that determines the animal. It's not the training you want to do that make dog or cat. But cats, as cats can determine the type of things you're responding to. If it's going to respond to your affection or respond to food, then if it's going to dance or not. Can you see now? So if you look at the relationship between the animal and the type of training, so the animal would be exposure, type of training would be outcome. But if you look at the relationship between the type of training and dance, the type of training would be the exposure and the type of the dance would be outcome. Can you see? So in that case, the type of training and the dance, they are outcome to the animal, while the animal and type of training, they are exposure to the dance. And you see, so we are talking of a relationship between variables. It depends on the variable. It's just like in the office, the supervisor is superior to the officer. So the officer will say, yes, sir, to supervisor. But when the director comes, the supervisor will say, yes, sir. So yeah, in that relationship between supervisor and director, supervisor is inferior to director, director is superior. There's supervisor and officer, supervisor is superior to the officer, officer is inferior. So it depends. So on the, but what we're not talking about no distinction, we have, I said that in some situations, you can use log linear to analyze multidimensional contingency table in a situation where you don't care about whether exposure, you just want to know there are many nominal variables, you want to see how they are related. That's what I just said. Now the question, I don't know if I've answered that question now, that person's question. So the second question.
Yes, sir, you have answered it, sir.
Okay, that's good. The second question by the other person talk about is it the same thing as 3 by 4? It's not the same. You know, the issue of 3 by 4 table is still 2 variable. It just means that one variable have 3 categories. For example, socioeconomic status, upper, lower, middle, upper, middle, lower. 3 categories of socioeconomic status.
Oh, I get it.
So
thank
while
you, sir.
education, you can have no formal, primary, secondary, tertiary. Can you see now? So it's 2 variable in that sense. It's only that they have different category, the number of category of possible outcome. It's only one person can belong to only once at a time. But for socioeconomic status now, you can only be in one category per time. Those are just possible value anybody can be. The same thing with level of education. So if you are looking at association between socioeconomic status and education, it's 2 variables, it's not 3. So I think you have answered that second question now.
Thank you, sir. Yes, sir.
That's great. Now, who was not clear about the response given about the how many ways we can pair 2 things, 2 variables, and how many ways we can pair 3 variables? Who is not clear? Because don't be shy, let's just, because all those little things may hinder your understanding. If you remember when I was in the lecture, you that were in lecture yesterday on the key to understanding statistics, I made mention of something, I'll be saying it. So when the key to understanding starts with the basic concept, all these parameters, statistics, differential, statistics, scale of measurement, and I made mention of something. Probability is very key to understanding statistics, and as you under the statistics, mean, standard deviation, and variance. Those ones, they are, if you understand everything with probability, everything about advanced statistics is about all those things. Mean, standard deviation, variance. If you remember when we talk about correlation, we say it's a standardized covariance. Well, we divided with standard deviation to get, we divided covariance with standard deviation to get correlation. How did we get in normal distribution Z? What do you divide? We divide with standard deviation. So a lot of things about standard deviation and variance, mean, standard deviation, variance. So the same thing. Some of those small things, very, very important. If you don't get it, so I think everybody has gotten it now. If it's not clear, let me know. So if it's not clear, the response they give, yeah, we have agreed. So somebody is making us. Please, if you are not answering it, there's not for you. Just mute yourself. So 3 main effects. What I just want us to look at is that so there are 3 variables. So each of them has effects. You call it. So main effect of each of the variables. Maybe. Then interaction effect. Interaction means those 3 variables. How many ways can you pair them? It's 3 ways. We have already said it. Look at it. Animal times training, animal times dance, and training by dance. Those are the 3 ways. So their interaction effect now, the 2-way interaction now, involving 2 of them, they are 3 separate. And it's possible also you can have animal trans training and trans dance. That is the highest level interaction. That is 1. So in the analysis you are going to do now, you are going to have main effects. There are 3 of them: animal, training, dance. Then 3 interaction effects of 2 variables. Of the 2 variables, can you see 3 of them here? Can you see? Then 1 interaction involving all the 3 variables. So we have 3 level main effect, 3 interaction involving 2 and 1 interaction involving. So here under the main effect there are 3. Under the interaction involving 2 variables there are 3. Under the interaction involving 3 variables, 1. And somehow you will see when we try to do the dummy. The dummy, I will explain it when we open the data set, because the way it is here now, it can be confusing, that I will explain. If you need to come back to see, but just know that in a log linear, you must create dummy 1 or 0, and it just happened that this example you give all the 3 variables. There are two categories. So you create one dummy for each of them. You make one, the other one 0. 1, the other one 0. 1, the other one 0. If there are 3 categories, like the one Hugo was asking, if there are maybe something like upper, middle, lower, we have already learned that we create 2 dummy for 3 categories. We're going to make one as reference. So in this one, there are two categories. Only one dummy. One is reference, the other one you create dummy for the other one. But if the 3 categories, one will be reference, you create 2 dummy, one for the other 2 groups. So let's proceed. Now, if animal training and dance are represented by A, B, and C, respectively, therefore the resulting linear, we just want to, before we run, want to see, since we are using linear approach, so just for us to conceptualize, how will it be if you use linear equation to represent it? So we have the outcome. So if you have the outcome now, you know that in linear regression, we usually have the regression coefficient. Even though we will not calculate regression, we just try to give mental picture of how it will be. B0 is usually the intercept. So you're going to have B1A, B2B, B3C. That's it. If you remember, those are the 3 main effects now. Then their interaction will be B4AB, B4AC, B6 rather, B4, B5, B6. This one to just telling you the different effects you are having, just like giving a serial number. The B0 is the intercept. That will be the value of outcome when all these exposures are not there. So the effect A, B, C, each of them, then the combination of the 2 effects of the 2 variables, there are 3 of them also, and the interaction effect of the 3 variables, A, B, C. I think it's very plus. This one is the error, because you know that they cannot. If you have been following us, we have, since we started our linear regression, you should not have problem understanding how this error comes in. So we may not be able to be explaining it, because if we are to be explaining everything now, what we are supposed to have known in the past, we will not have time to do what we are doing now. And that is why I actually encourage people listening to the what we have done. They are all recorded, listening to the what we have done, and you will be able to understand. So since the variables are categorical, the outcome should be in terms of log. So if you say ln, natural logarithm of outcome, will be this, just write it like this. So this one, you put the natural logarithm of error here also. When data are categorical and we include all the variable terms, main effect and interaction effect, we get no error. Our predictor can perfectly predict our outcome. You're going to see when we run all these things I'm talking about, you're going to see when we run it. No, if we are dealing with categorical variable and you code them very well, you will not see error. If all of them are present, there won't be error. If we start with because the reason is very simple, is taking either yes or no, there or not there, 0 or 1. If we start with the most complex possible model, we get no error. The job of log linear analysis is to try to fit a simpler model to the data without any substantial loss of predictive power. Then therefore, log linear analysis typically work on the principle of backward elimination. So you may not appreciate it when I will explain this one further when we start running it now. So it uses the principle of you load everything. If you remember during analysis, linear regression, multiple regression, we talk about forward and backward. But this one use the principle of the backward. In the sense that in the backward, you load everything, you begin to remove. If you remove anyone, and if it doesn't change, maybe if it is linear regression, it doesn't change your R square significantly, and that shows that it's not a useful something. That's why you remove it forever. You just discard it, it's not part of the model. But if you remove something and it changes drastically, you return it back because it shows that it's a good factor. So that's how you'll be removing each of them. The one that changed drastically would be a good factor. The one that doesn't change it is not a good one. This one uses the principle of backward elimination. Now, to test whether a new model has changed the likelihood ratio, all we need to do to take the likelihood ratio statistic for a model and subtract from the likelihood ratio statistic for the previous model. Well, this one is just an interlude, and just to explain what I'm saying. The statistic you're going to use here is the likelihood ratio. If you remember, we said that this one is an extension of chi-square. If you remember, when we calculate chi-square, there's a form of chi-square. Apart from Pearson, we have likelihood ratio chi-square. So this is the logic, because that one use logarithm to calculate chi-square to arrive at the same. It's only that the value that actually gets is usually slightly different from the one gotten through Pearson. It's the same thing. So when we run, in fact, the first thing is for us to first of all run the chi-square with this data. You see the likelihood ratio chi-square also before we proceed to do log linear analysis. So what this one is saying is that if you load up the whole model and you remove one, what you are looking for is that if that particular variable you remove significantly change the likelihood ratio, which is the statistic being used, the likelihood ratio will be significant, the change will be significant. That's what it means. Now, since log linear analysis is an extension of chi-square, it has similar assumption. So before we run it, we'll just quickly look at some of the assumptions. The entry should fall into only one cell of the contingency table. Well, that one, everybody knows that one. Then in log linear analysis, with more than 2 variables, it is already all right to have up to 20% of cell with expected frequency less than 5. You remember the assumption of using chi-square. The expected value, you can have expected value less than 5 in up to 20% of the cell is acceptable. But once you have more than 20% of the cell with expected value less than 5, chi-square is not valid. So one of these is that is what we are saying, that 90% in 80% must have expected value of at least 5. So the remaining 20% may have expected value less than 5. But once we have less than 80% with expected value up to 5, or in another way of saying it, more than 20% of the cell with expected value less than 5 is not valid. Or if there's any one cell with expected value less than 1. It is an assumption for log linear. So if this assumption is broken, the result are radically reduction in the power. So if the assumption is not met, you cannot, the power of the test is reduced. What it means that when you say there's a reduction in the power, you will find something is not statistically significant. It may be that the power maybe is not true because the power has gone down. Maybe in that data set it's supposed to be significant. It's not significant because the power is very low. So your power is ability to detect is different if it exists. So the logic, what you can do if you know that one is violated, the assumption is that violated, And that is what we do also when we do our chi-square. We may collapse. You may collapse. You may remove a particular variable completely. In this situation now, how do you remove a variable? You may decide to, okay, like we have 3 variables now. We talk about animal, training, and dance. So you may remove the training from it and just say animal and dance. I just assume that you have trained them. You will not forget about the type of training you give. Okay, you have trained cat and dog. How many or what proportion dance or not? So, because you know the logic behind it is, let me go back to the table. Let's say now you have some value are very scanty to the extent that if you calculate the expected value, it will be less than 5 some cell. What will happen is that if you try to collapse, you remove the issue of training from it. So it will jack up, it will reduce the number of cells, it will shrink it. In fact, it will end up with 2 by 2 table. Because this one is giving you 2 separate 2 by 2 tables. But that one will end up with 1 2 by 2 table if let's say you remove training from it. So the implication of that is that you now have enough number in each cell so that the expected value may be now the jack up. So we will have the issue of expected value less than 5 in most of the cells. That's the logic behind removing a particular variable completely. Another thing one can do is to collapse some level of variable. You know, collapsing data across one of the variable, meaning removing the variable, but collapsing level of one variable. For example, if we talk about maybe when we talk about socioeconomic status, you can decide some people can just say upper lower and just remove the middle and say upper lower. Instead of having 3 levels, you have 2 levels so that you can shrink. People do it a lot. For example, if you have like a marital status now, where you have majority are married, there's some are single, the people that are separated, divorced, widowed are actually scanty. So when you have about 6, 5 levels like that, some people decide to collapse separated and divorced together, separated or divorced, so that you can reduce the effect of not having enough in a particular cell. That just is the same thing. So you can collect more data. You increase the sample size. If you increase the sample size, what will happen? It will jack up the number in each cell. Then you can accept the loss of power. That is, you just take the result like that. Loss of power means that something that will have been significant may not be significant. Those are the different approaches to it. If you want to collapse your data across one of variable, then the certain thing has to be considered. I think I've talked about I've talked about it. A part of it, not all. The higher order interaction should be non-significant. I think this one, you understand it better when we run it, because some of this discussion will now come back when we run it. You see the meaning of higher order interaction. The level of interaction I discussed the other time here, the highest order is animal times training times dance. That's the highest order interaction of the 3. If let's say there are 4 variables now, interaction of the 4. If you have 4 variables, you're going to have many levels. Apart from 2, you're going to have 3 interacting, 4 interacting. You're going to have many levels of interaction. But the highest order here is animal times training times dance. The next order will be animal times training. So those are the 2 levels of interaction. What are the main effects? There is no interaction here. I don't know if there's any question. So we want to, so that we quickly go to analyze. This one is showing, if you want to go and do the analysis, this is how you go. So who will share with us Or before that, any question of what we have just discussed? We are going to have a lot to discuss when we run it also. Any question? So it's very straightforward.
Just go ahead.
Okay. So who will share with us? Because if you want to go to do the analysis, now you go to log linear. We will first of all do cross tabulation first. Then we'll go into log linear. Then model selection, select variable you want to include, the analysis, then a lot of things. If you go to, they are written here, but
I can share.
Okay. Okay, share. Okay, let me start sharing. Share dog, cat, dog dance. Dog, I don't know, maybe dog, cat, dog dance, or dog, cat dance. That's the name of the.
Can you enable me? Enable me to share.
Sorry. So I've done that now.
Okay. Can you see the screen?
It's coming.
Okay.
Okay, that's fine. Yes.
Okay, sir.
So go to, if you look at it, you see the animal. If you scroll down, animal, you see cat first, followed by dog. They are arranged in series. Then training, food as reward first. Scroll down, let's see. Let's scroll through it, let's see. Is it the memory of the computer that? Or is the RAM? Maybe it's the RAM that is very
slow.
Okay, no problem.
I think so. I think it's the bandwidth.
Okay. What I just wanted to tell you is that they are arranged in series. So you can click on the variable view. Let's see the way we did the coding. Click on the variable view.
Okay.
Okay. So click on that first one, animal. The value. Can you see? The dummy. This is the dummy now. Since each of them is two categories. Cat is coded 0. Dog is coded 1. You can make cat 1, dog 0. So it doesn't really matter. No, it doesn't really matter. But just no. Okay. Check the other one. Training. Food is 0. Affection 1. Yeah. Dance. Yes, 0. No dance 1. That's for dance.
Okay.
Yes, that's where we created it up. So you can go back to the data view. Go to view here. You see, if you remove the labeling, you see the code in front area. View. Beside edit, between edit and data. Click on it. Click on value labels. Can you see that? So what we code is there. This is what we enter. Why is showing yes or all these cards is because of the labeling, and we now say she show us. So by the time you scroll through, you're going to see the way we label it. Okay, I think all of them are 270. 70 dog, 200 cats. Okay, we can, let's first of all do cross tabulation. Let's do cross tabulation. analyze, cross-tab. Okay. We move row, make row the training. No, make row the training, type of training.
Okay.
Yes. Then dance column.
Okay.
The animal, make it level of the. So you are like a layer. You are doing more like certify now. You get it down. You are doing separately for animal and for each of them. We just want to explore. So you can click on statistics. Click chi-square. Close it. Close it. You can put cells. Row.
Yeah, interested in row, okay.
Row, yeah.
Okay.
Just say continue. Let's just see. We just want to see the before we go into the linear to explore it. What is going to you have to stop sharing and share the output. Yeah, you share the output.
Okay. I'm sharing.
Yes, it's coming.
Okay.
Thank you. So if you check, if you scroll down, if you look at the you see that it is for both dog and if you look at it, the association between the type of training and the dance is highly significant with cat, but it's significant with dog also, but not as much. Look at the p-value, not as much as the cat. Overall, it's significant. If you go back to the table, sir, go up back to the table. We will go back to the table. You will see. We will look at the percentage that look at cat. Food as reward and affection as reward. If you look at which proportion does more, you see with cat is food and reward 73.7 dance. Like reward 29.6% dance. But if you come to dog, you see food as reward 58.8 dance, affection 80.6 dance. Give you a clue. Like dog will dance more for affection and food. While cat, unless you release food, cat will not dance. So there's no so that one is food. So that is what it's telling us. So we can let's go to the log linear now. You can access it from here. Go to analyze. Log linear. Model selection.
See general, which one?
No, model selection.
Okay.
So the factors, all of them are factors. Move all of them in. So you see that he put question mark in front of each of them because how do you code them? Define range. Click on define range. Click on it. Minimum is 0. If you look at the way we code is 0 and 1, maximum 1. Continue. Then click on that model. Let's see what is it.
Okay.
Model. Build item. Okay, let's leave it as saturated. Let's leave it as saturated model. Okay. Let's leave it as saturated model first. Maybe. Go to options. Click on option. You can click on parameter estimate. Click on parameter estimate. Association table. Click continue. So click OK. So you scroll down so that we see the result. And yes. So let's see the first table, the way they are coming. Let's look at the table, the way they are coming. No, you have already, yes. I think from here, not from here. Let's see this, yes. You will see, let's see this first table before there's a table. You are pass it again.
Convergence.
No.
Warning.
It's okay here. Information. You will see now it tells you that 217 cases. I say the animal category, just summarize the way your data is 2. Each of them 2, 2, 2. Each of the category of each of the variables is 2, 2. And there are 217. No one is missing. Okay. Let's go to the convergence. Okay. Okay. This one just telling you about iteration. Just go to the next one. Cell count and residual. You will see, what do you see in the cell count? If you see the first table we show, though even in the cross tabulation and the table I used to present it, you will see there are 28 cats that see food as reward, and 10. You know that a number of cats under the training is dance is 38, if you remember. 10 food as reward, in 28 food as reward, 10 food affection as reward. You see that he gives them, but you will see 0.5, 0.5. It just added, it's the same, the frequency of each of them, but the only 0.5, if you want to know the origin, if you don't want that 0.5, it's just the way the computer runs. If you don't want it, I want to show you. I wanted to tell you when you were running it. If you remove it, go back to that. So I just want to show you. We are not running anything. Just go back to analyze. Go to that log linear. Model selection. Click on be under the model or other.
It's option.
No, it's here. It's not here. Option.
Is it this one?
Option. No, it's not that one.
Okay.
It's
Yeah,
delta.
option.
It's delta. Option. Click option. Can you see delta is 0.5?
Okay. Yeah.
Examiner. So it's just one of the two used for convergence. So if you don't want it to appear, you can reduce to 0, but it doesn't. It's just adding that one for it to it. Just like the way this thing had for continuity correction, whatever. It's just for calculation. So
Okay.
just cancel. I just want you to see the origin of that 0.5. I've been added to each of the count. Now let's go down. So there's this goodness of it, this likelihood ratio chi-square. Just like the likelihood ratio chi-square you do, it's trying to see if, look at it, because it's a perfect fit. Perfect fit, all of them, if you look at the other model, say saturated, it's a saturated model. You understand me now? I don't know if you understand me now.
Yes.
You know that if this model is different from saturated, it will give you a value, higher value of chi-square, even to the extent that it may be significant. But here now, it's giving you chi-square is 0. What you are seeing here now is significant. It tells you that you cannot even calculate it. It doesn't exist. There is no difference. It's a perfect. It just tells you it's a perfect model. You understand me now? Everything fits into it. Now, let's look at K and higher order effect. So if you look at under K, you see it puts K and higher order effect. You see, if you see that A after K, A, let me see if I can pick my annotation. Okay. If I'm not the one, if you are not the one sharing, it doesn't. Okay.
Okay.
And don't worry, just wait. I'm just using the arrow. You see, test that K and higher order effect are 0. What is higher order effect? You know, this K 1, 2, 3. Now, K way effect 1, 2, 3. This one K and higher order effect. 1 is May effect. 2 is the interaction effect of 2, and 3 is the interaction effect of the 3. Are we following now? You try to say, okay, the chi-square for the interaction that is associated interaction between training, dance, and training, dance, and animal.
Animal.
Yes, look at it. It's 20.305 chi-square. Can you see now? It's saying that there's an association. I don't know if you understand. There's an association between the 3 of them. Now, this number 2 is telling, when you say K and higher order, the first one is telling you, is there any association for between main effect plus all the higher K and higher order effects. So number 1 talk about all of them. Is there any association in the main effect? And all main effect mean that the animal, the training, and their interaction. Both interaction in two-way interaction and the 3 interaction. That is, two variable interaction mean training and dance and animal, and animal and training. So that is what is, and the 3 combined together. That is the first one. Why this second one? And it's significant. That's an association. Then the second one is talking about 2 interaction of 2 and above. Interaction of 2, that is training and dance. dance and animal, training and animal, plus training, dance and animal together. Then the three is just talking about the three of them, the higher order effect. The way they arrange it like this is that in saturated model, we first of all look at the higher order effect. Is there any significant difference? That is, when you look at the association between training and dance and animal, you may have there, and for you to even say that you have higher order effect, there must be a lower effect. So that is why they arrange it like this. Then look at the next one, K effect. This one is not K effect, and this one is K effect and higher order effect, but this one is K effect. This one is telling you, number one is telling you the interaction at the level of main effect. Is there any association? That I don't know if you understand me now. This is 1, 2. If you look at it now, the chi-square is not up to this one. It's 1, 2, 7, and it's still significant. Then this one, interaction at the level of the interaction effect of two variables. Is there any significant also? Then at the highest level, if you look at something like this number 3 and this number 3 is the same. Why is it the same? That's the only one that is the same. I want us to know, I want to be sure that some people are not sleeping where they are. I want you to talk. Why is number 3 and number 3? Why is it the same?
Because they are the same, because they are testing the same thing.
Yes.
That's the highest effect.
Thank you. That's the highest effect.
All the three.
Yeah. That's the highest effect.
I'm really lost though.
That's why I asked the question. So where are you lost?
You know, when you explain the K-way and the higher order, like I didn't, because I wanted to know that one. You know, your pointer was not showing. Maybe you didn't know that it was not showing.
Once is not mean that this in the pointer.
Can you share that, Dr. Dolapo? Is it possible for you to? I mean, maybe you share so that we can.
Okay. Stop sharing. Let me go and read my own and share.
Okay.
Stop sharing. Let me read my own. Let me just read it out. Just 1 minute. Training. Let me share now. So this is the data set. You know, you remember it's because I didn't show the something here. So I don't like showing the value like that. So analyze log linear model, move on, define range 0, 1, continue, option, saturated, this, that's all. Let me share the output. Can you see? Can you see it? Please, somebody should talk if you can see.
We can.
Yes, yeah. Sir. Yes, sir.
Okay, this is where we were discussing there. Let me. Yeah. Yes. So what we are saying is that if you remember, we talk at the main effects. Each of those variables, they have their own main effect. Then interaction effect, there are two levels of interaction effect. We have the interaction of two variables, and there are three of them. Since there are three ways we can pair three things, there are three of them. Dance, animal and dance, animal and training and dance. So that are the two, that's the interaction of two variables. Then you have interaction of the three of them, which is the highest order. So the number one here is the main effect. Number two is the interaction of two. Then number interaction of three. Yes.
Okay, so when you say the main effect, is that the three?
No.
The main effect is number one.
No. What I mean is that when because I'm trying to qualify that main effect. Do you mean the interaction of like the ABC?
So the interaction.
The effect of animal on the whole show.
So yes, all the interactions.
The effect of animal on the whole show, and the effect of dance.
The effect of training, animal.
Training, separate on each of them separately. Those are the main
everything.
Effects.
So
okay, don't worry.
So the effect of animal on training.
Don't worry, just wait.
Okay.
Because look at this. Look at what we showed before. Three main effects. Can you see?
Okay.
Three main effects. Animal. The main effect is talking of the effect of animal, the effect of training, the effect of dance on their own. Each of them on their own.
Yes.
Interaction effect, the effect of where animal and training interact. The effect of where animal and dance interact. The effect of where training and dance interact. And there are three of them, three interactions involving two variables. Then we have one interaction involving all the three variables. Animal, dance, training, dance. So when you see number one is this animal training dance, that's the main effect. Number two is these three interaction involving two variables. Number three is this one, animal training and dance.
Okay. So that means that K.
So what he's saying is that to be sincere with you, if animal does not have effect, the interaction of animal anywhere cannot have effect. If training does not have effect on its own, the interaction cannot have effect. If dance cannot have, it does not have effect, interaction cannot. That is why they use elimination. They can have, I don't know if you understand me now. So you may, in backward elimination, the first of all start to eliminate the higher one because they can be animal and training and dance effect, and there's no interaction at highest level here. I don't know if you understand, but you cannot have interaction at highest level without interaction at lower level. You understand me now?
Yes.
So let me go back to that one now.
Okay. So in that output table now, because I know I'm seeing them as 1, 2, and 3.
So that this
I
one,
want to know what the one represents. Okay.
What just, if you look at it, okay. Let's start with this one below, K effect, K way effect. One here just means animal on its own, dance on its own, and training on their own. Each of them, do they have effect? This is the effect.
Okay.
It's significant. For the fact that the chi-square is high and p-value, it means that they are effects.
Yes.
So number two, where they interact as per, later we're going to see where the effect is going. Where the effect is another way table. You see where the effect is. But just telling you, is there effect at that level? Yes, I'm now. Now when we say animal, it may be that maybe animal are more, cat has more effect than dog. All those stuff. Now, number two now is talking about training dance, animal, and animal dance. That is the interaction of two videos. That's number two. And that level also is significant. Can you see? But you will see that the chi-square for the main effect is higher. You expect that. Because before there can be interaction effect, there must be main effect. If there's no main effect, you cannot have interaction effect.
Okay.
But you can have interaction effect and you can have main effect without interaction effect. Examine now. Now,
Yes,
the last one is the highest interaction, which is the three of them. Is there any effect? And it's still, even though the chi-square is low, but it's still significant. You examine now.
okay. Yeah.
You understand? The upper one, what you just done, the upper one, the K
Yeah.
and higher order. What it does that at this level, is there any significance in both at that level and the one up? They capture everything together, including these 2 and 3. K-way and higher order effect. Can you see now? That's why the thing is very high. It combines all this together. That is, it's telling you that at this level, is there any effect? At this level and up. Then these 2 combine the interaction level and the higher interaction level. And this one is the highest one. This is the highest one, is just the single. That is why this one is the same thing as this here. That was the.
Oh, I now understand.
Okay. That's why it's the same. That's the only one that is the same there. The other one can never be the same because this one, these 2 combine this level and level 3. Why this one combine all the 3 levels? But of course, this 3 is only the 3 level. That's why it's equal to this 3 level here, level 3 here, the same thing. Yeah. Now, partial association. Can you see now? It's not trying to bring it down. When you are not talking of animal and training. Can you see? It's significant also. Can you see? You now say, association between animal and training. You know, the other one is combining all of them together. They start to split it now. Animal and training. You know, they don't need to put animal training and dance because these ones has already told us. These 20.3 already submit that animal training and dance because that is only one. The other one, there are 3 in each level. I don't know if you understand me now. So you want to separate them because what this one just tells us that at that level is significant, but we don't know which one is significant there. So look at the animal and training. There's an association between animal and training. Can you see now? Then animal and dance is significant also. Can you see? Training and dance is significant also, though it looks less significant, but it's significant. See, then animal is significant. Training is significant. Dance is not significant. I don't know if you understand me now. People and I want people to ask questions because the way people are. Do you understand that now?
Understood, sir.
Okay. Is that the consensus? Understood? Is that
Yes.
a consensus? Okay. Now.
Yes,
Somebody was talking somewhere.
No.
Okay. This one is just showing the parameter estimate. You know what I mean by parameter estimate? He now try to quantify it by doing Z. You know, we have chi-square here. You know that chi-square and Z, they are related. Z distribution and chi-square distribution, they are related. People are not answering. Do you know that they are related?
Yes, we're following.
What did you say? Hello?
We are with you.
Chi-square and Z, they are related.
We are with you.
Yes, sir.
Chi-square and Z, they are related. So if you remember, the origin of chi-square is square of Z distribution. And also demonstrate that when you are running a logistic regression, when you get word statistic, when you get your beta regression coefficient, you also get the standard error. If you put the beta over standard error, it follows a normal distribution. That is Z. If you square it, it follows a chi-square distribution, what they call word statistics. So the same, if you run the same logistic regression with what do I call it? Epinfo. It gives you Z. It doesn't give you chi-square. It gives you what statistic. It stops at the level of beta divided by standard error. While SPSS square it and gives call it word statistic. So to show you that they are actually related. So this one is just trying to show the Z and also try to give you confidence interval of it, right? And the reason is very simple. The reason is very simple. Why you cannot give confidence interval with chi-square is that since you have square, it has removed negative. In the distribution, you can have negative side and positive side, both sides. But chi-square, you don't have. It's skewed to one side. It's not symmetrical like Z. So with chi-square, you cannot be talking of 95. Difficult to calculate the confidence interval. So that is why just this one still present the same thing in different way. But if you still look at it now, which one is not significant there? Okay, with this one now, it says that even dance is significant here, because that's what it's showing. Then
Dance
okay,
and training
yes,
is not
yes,
significant.
it's now, yeah. What did you say? Dance and training.
Dance and training is not significant.
Exactly. Dance and training is not significant. You see, yeah, it's showing that dance and training is not significant. And when you look at it also, there are the difference here. Because this other one that is significant is either plus to plus, man, it doesn't cross zero.
It doesn't cross zero, yes.
Yes. But it's only dance and training that cross zero here. So what is pointing to is that when you see that there's down, you know, it's just like we are trying more like triangulation. The analysis is like triangulation, tries to look for different way to find out. So we have already found out here that there's issue with dance. So that issue with dance, it has to do with what? It has to do with training. You're going to see the results, final results. You're going to see. It has to do with dance and training. Where then now the backward, this one just showing the backward elimination stuff. Now I want us to go to this last one. So if you look at this table now, this is the table. If you look at the table I showed before on my on the what do I call it? On the PowerPoint. Now, if you remember the first of this table down there, it has 0.5, 0.5, 0.5. But this one, this is just the perfect count. Now, look at it. It's trying to show you the observed and expected. But you see that the observed and the expected, they are all the same. Can you see the observed and the expected?
Yes.
Yes, we can.
So all of them are the same.
They are the same.
Yeah, it's just it's showing you that it's a perfect fit. The observed and expected are the same. Now you may not think, okay, how do I interpret the whole show? Now, if you come down to, let's now rerun what Dr. Yemi ran the other time, the one he ran to look at where the association is. Now, let's go back to analyze. And what he did also, there's another way you can do it too. If you want to separate that thing, you can differ. Apart from what he did, you can go and split the file. Yeah, I think the one we did was okay. If you want to, let me just, so that we know that we have been using it before. Data, go to data, split file. Just click on this thing. You want to split by animal. So if you now say analyze, cost tab, training, dance. So anyway, we don't even need it. Let me just put So let's look at what we have here. You will see that the total is 200 for cats and total is 70 for dog. Now, you see that out of look at the percentage that dance among cats. Look at the percentage that dance among cats. What proportion dance among cats? We have 73.7.
38%.
Then 29.6. No, sorry. The proportion that dance among the group that receive food as reward. I receive food as reward, 73, because the total that receive food as reward, they are 38. While 28 dance, 10 did not dance. So 73.9 and 7 dance. Well, I want the total that receive affection as reward, 162, 48 dance, yes, which is 29.6. It shows that the cat are more likely to dance when they give food as reward, not affection, more than affection. So if you come to dog, you will see that the total that dance respond to food, they are 34. And the that receive food as reward, 34, and 20 dance, 58.8. While the total that receive affection and reward is 36 and 29 dance. So 80.6% of dog, as opposed to 58.8% of them, they respond to affection by dancing. Can you see now? So now what you can do, you can actually cross-check. We can actually, okay, let's do something. Let's try to look at association between, without splitting, without bringing dance and animal. Let's just look at association between dance and animal. Let's first of all forget about the type of affection they give them. So, you know, I have to go and remove that split. And that is why the other method is better. Instead of using the split, instead of using the split, we just use what we did before. So analyze
layer.
Yeah, you use layer. Descriptive, cross tab. So want to remove, let's put animal instead of, want to see animal and dancing. Of course, you can see, of course, there is a good association there. But let's see, between cat and dog, who dance more? I want you to respond. Between cat and dog, who dance more?
Dog dance more.
Dog dance more. Yes.
Dog.
Yes.
70%.
Yes. Dog dance more. When you look at interaction between, if you look at it, when you know the other one, we run all of them together, but now we are trying to separate the running, because what Lorena did was to run all of them together. But for you to understand the way that result comes, that's why I'm trying to split it into pieces like this. If you look at it, we have already established that there's significant interaction between animal and dance, right? So the interaction there is that a dog generally dance more than cat. And it's
that significance that was established, was it based on the likelihood ratio?
What did you say?
You said that there was this significance that's just for this table now. You said we've established that there's a significance. I know that when you want to say that you want to establish that there's an association, you have to use the.
No, that's not what I said, because
is there a likelihood ratio or?
If you look at it, that one, I'm just using, the issues there is that we have already established the fact with that log linear that with the likelihood ratio chi-square they used here, there is significant association between animal and dance. Yes, sir. Where we have some issues about training and dance, little issue about training and dance, animal and dance. Now, here, I'm just using this one to confirm. Normally, when you have a table, how will you to interpret it by your own percentage? Actually, we don't actually need this significant here. It's the percentage we use to explain. But I just put this one as just a confirmation. We don't actually need the significant here. It's just for us to rearrange it to say, okay, let's even look at animal and dance to see. Yeah, how do you interpret it? Who will you say dance more? If you are looking at interaction between animal and dance, dog dance more than cat.
Yes, sir.
So let's look. Without splitting it also, let's look at the training. Yes, sir.
So, like all these chi-square that we have here now, which one is the best to use to interpret this table? We have percent chi-square, we have continuity correction, we have likelihood ratio, linear by linear, and all of that.
You remember now when we were doing our chi-square class, we talk about people that talk about continuity. They say that if there are some, we are dealing with 2 by 2 table, and there are some cells that are very expected value, maybe less than 5, some people say less than 10. Yes, I mean, for continuity.
Yes, sir.
While some people say that even once you are doing 2 by 2, just do it. Some people say you don't even need it. Can you see now? The issue of continuity is different. If Professor Yates that recommended, some other professors also say that there is no need. There is chi-square is already a conservative test. When something is a conservative, it has given room for a wide margin. So there's no point to even using any continuity. That's what some people say. To me also, I don't even see anything because people just used to play prank. For example, now if you look at it now, if not because of the chi-square is very the p-value is very low. That's why you are seeing so. But if you look at continuity, the value of chi-square is small than the person. If let's say now at the border and the degree of freedom is 1, you know the critical value is 3.8 or around that value. If let's say the chi-square is around 3.8 something now, that is just barely significant, you may discover that the p-value for the continuity correction may be 0.056 or 51, 52. No, a little bit. Why the other one just 0.05? So many people, whenever they encounter that problem, they choose the person. Since the continuity correction is not more significant, they choose the person. But if both of them are significant, they say they choose continuity correction because they know that whichever way, what's the difference? Either you choose it is significant or not. So that's just it. The issue about me, I don't believe in that continuity correction also. So that's the level of argument about it. Now, likelihood ratio, if you look at the value, is just slightly higher than this. Is the formula I use to calculate that differ. The people use person is the commonest. So they are actually saying the same thing. So if you look at linear by linear association, that one is done. It's just because computer is garbage in, garbage out. You have to program everything there. That one is not useful in this setting. It's only useful when your exposure level, the outcome is 2 categories like this, but exposure is more than 2 categories and it's ordinal. Like that your data set. That
trend. Okay.
And where we have the issue of years, we expect where we use year as ordinal because we expect a progression every year.
Okay.
So you can treat each year as ordinal variable. Because you know, just like the way they look at inflation, they believe that things must change either to become worse or become better each year. That is one.
Okay.
Then you talk about level of facility also, which you have primary, secondary, tertiary. So those exposure, they are ordinal. In that case, you can use chi-square for trend. In fact, that's the bailout. There's a lady going for exam. Ugo.
I'm here, sir. I'm here, sir.
So you know that lady that you met on the Zoom, that Ango, that your friend?
Yes, Juliet. Yes, I know her.
So she did the analysis and she was having some issue. The issue was that when he did something, he did cross tabulation, the chi-square was not significant. He now used the thing for logistics. The thing was significant. He now say what causes the significant? He was confused. So when he brought the result, and I say he should share the data and run something. When he ran, and I discovered what the problem was. The chi-square like this because he has age category 1, 2, 3, 4, maybe about 4 categories of age.
Okay.
To cross-tabulate against something that is yes or no, whatever. So with the result, the piercing was not significant. But the trend, the association linear by linear, which is chi-square for trend, was almost significant. It was 0.05 something, 54, something like that. You know, 0.054. You know that there's no difference between 0.05 and 0.05. That's why sometimes when you are doing regression, anything that is 0.0 something, you include it in the regression. Because the age you categorize, the way you categorize your age has effect on your outcome. If another person they categorize the age, you may not get, if you cross-tabulate, you may not get the same answer. Right? And when you are doing regression, you feed in the age directly. Right? So sometimes that is why whenever it is close to 0.0, you go and include it in the regression. So therefore the piercing chi-square for her, it was the p-value was 0.2 something. Therefore the trend is 0.05 something. So that was why when she now did regression, the thing was significant. So you must understand the data you are dealing with. So that when you are having exposure that is ordinal, you should even look, more important than piercing is chi-square for trend. Because your interest is what this thing, does it change along the level of education? Does it change along the socio-economic level? Along the age? You know what mistake people make is that when you categorize your age, it's not just nominal variable, it's an ordinal variable. It's an ordinal. Anything quantitative you categorize has become ordinal, right? So you cannot just run chi-square and be looking for piercing, especially when the category is more. Something can be ordinal when the category is more than 2. If you categorize your age into 2, it's not ordinal. But when you're not categorized to 3 or more, it's ordinal variable. So more importantly, there is the chi-square for trend, which SPSS present as linear by linear. So that one. So I want to quickly run I want us to run again, in this case now, the training and the dance. And let's neglect the animal. Let's see. If there's any question, please, people should let me know.
When do you want to?
Any question?
No, sir. So
okay.
just to confirm, so that means for this analysis now, what we're interested in is just the value, not this table that shows the different
Yes,
types
what we
of
are looking at is, yes, we are trying to more like going, rearranging it to see the way the percentage go. We have already know that even the training and the dance, there's a significant something there.
The other thing I
Yes.
wanted to ask, because I noticed that you are using those terms interchangeably. Is there a difference between association and relationship? You kept on talking about association between this and the relationship between this and this. Is there a
And when
difference between those two?
is a school of thought, let me tell you, some people will say that there is association, there are difference between relationship and association. People use it the same way. Sometimes people now try to differentiate when they want to, especially if you want to differentiate between correlation and regression. You now say, okay, correlation is talking of association, while regression is talking about relationship. It's just for you to know what each of them is doing. Because somebody else can be using it interchangeably as the same thing. While some people say they are different. They say association is a more shallow something, while relationship is deeper. But the description look more social than statistical because the way people use it, people use them the same way. So it depends on, that is why that's why we talk about operational description. That's why even if you present your paper, if you present paper, it's good for you to say, okay, keywords. This is what association means. This is what, if you are talking about relationship, this is what you mean. Because so in another person may write something and he may say association. Another person may write something and say relationship. And they are saying the same thing. They mean the same thing. Right? So that's just it. So if you the research does not belong to one person alone, and it doesn't belong to one field. You go to other field, like for example now, the word correlational study. Correlational study is in medicine that we talk about correlational study, the ecological study, the way we think about it. Outside medicine, what you call descriptive study is what they call correlational study. One, they just want to see, okay, the association between cat and dance, animal and dance. They say they are correlating animal and the type of training and the dance. To them, it's correlational study they are doing. But in medicine, in epidemiological study, that's not correlational study. Yeah, it's not correlational study because in medicine we are more quantitative. And let me tell you that the people that develop statistics over time are biologists, including you as doctors, and social scientists. So the people that are more, I can tell you that people that are more sound in statistics, they are operationally, they are biologists and social scientists. So every other person, all those history or whatever they call it, chemistry or all this natural science and all those arts, the way they just, in fact, in law, they don't do quantitative study in law. It's now they want to introduce it. They don't do quantitative research. The qualitative they do. So one lady came for my training, a PhD student in Faculty of Law in University of Maiduguri. He came to Abuja for training. She's doing research. They say they are now introducing, they are now encouraging them to go into quantitative research now because it has been qualitative research they do in law. They have not been doing quantitative research. And it's quantitative research that requires statistics. So can you see now? So a lawyer can do a research now and say it's correlating this and this. You know what is correlating is different. It doesn't even know anything about statistics. But you use the word correlation. The word correlation is different from what you know. If you say it's this correlational study, it's different from what you do in medicine as correlational study. It's the same thing with the word association and relationship. So you just need to understand the context. I don't know if I have. So here now, what I just want us to look at is that which one dance more here? Food as reward or affection as reward?
Food as reward.
Can you see food as reward? So, but a lot of things, you know that there is a confounder here now. The confounder now is the animal. You get me now? Because here now, food as reward dance more. Then when we talk about animal, dog dance more than cat. Yes, I mean now. But the dog dance more than cat. But food as reward is dance more. Yeah. So what make dog dance is different from what make cat dance. So when we now split it into dog and cat now, we now see that for cat, it's food that make cat dance more. While for dog is affection that make dog dance more. Are you seeing now? So you will see that by doing this type of analysis, it can even mislead you. Just this type of analysis alone. I mean, it's okay. Yes, food as reward is what make animal dance. Yes, I mean now, food as reward make animal dance very well. But until we separated it and do more like stratify analysis, what we did, stratify analysis, you now discover that food make cat dance more, while affection make dog dance more. Yes, I mean now. And that is why what the Loughlin analysis just put everything together to see. But the interpretation is now left for you. So if you want to interpret it, the best way is what we have already, the way we separated it, where we run this crosstab separately, layer by layer for each animal. That is how you can interpret it correctly. So in this case now, you do it separately for the animal. Yes. So when you do that now, you now know, okay, yes. Though even the issue there is that even this last one I did by collapsing, if you do it like this, it gives it to you also. It gives you the scenario for cat, for dog, and for the total. Yes, look at it. This is the table. Like if you want to show your result now, this is the table you show. Apart from the statistics you gather from the log linear, you just have to show this table. Show this table in your result. And that's okay. You now interpret overall, we have more of dancing with food and less, I mean, the people that dance more respond to food. Then you now look at the percentage. Then you now say, okay, even okay, who did we animal and okay, there's one we have not done. We have done animal and dance, right? We say dog dance more. Which one have we not done? No, there are three levels of interaction. We have not done one. We have cross-tabulated animal and dance. We are cross-tabulated. Okay. Okay, it's affection. Okay, let me run that one. Does that one even make any difference? Let's run that one. Let's look at affection. Affection will be the outcome variable. Animal will be the exposure. Affection. Let's see the result. You see? So which type of training that is more here? Okay, for food as reward. Okay. Food was even given to dog more as reward than affection. No. For both of them, the affection were given more, but the level of the food as reward in dog is higher than that cat. You will see that whichever way we do the analysis, you can see significant result. It's confirming what we read that we did at all the level there are significant interaction. I don't know if there's any question. If there are questions, some people are silent, some people are not contributing.
Yes, I want to see that. Yes, I want to see that the last table you just said now.
The last table.
You said something that the last one you just did now. You said something about food and that the dogs got food. Because from what I'm seeing, no.
But your voice is I'm not hearing you very. I don't know. It's loud, but it's blood.
Okay, so is it better now?
Yes.
Hello?
Yes, it's better.
I was saying that this last table you showed us, like I didn't get, because you were saying something about dog food as reward, but what I'm seeing here is under food as reward for dog. I'm seeing 48.6%, which is higher than
we are saying this. We are saying the same thing. That's what I said. I said we just try to look at animal and the type of. But this one, if you look at the type of training they give them, actually it's not actually the final outcome. The final outcome is whether they dance or not. But this one just try to tell you, try to relate the animal to the type of training they give. So if you look at them now, for each of them, for either cat or dog, more of them were given affection than food. But the percentage of dog that was given affection and I was given food is more than the percentage of cat that was given food. I don't know if you understand me now.
I do, sir.
That's what I just say. So that is why this one, and it means that it's significant. The difference that this is significant also. If you look at the logging analysis we run, we have interaction on all the levels between animal and training also that is significant. It shows that there's a significant difference in the distribution of the type of training they give them. I don't know if you understand me now, type of training. Yes. So what is telling you is that more of dogs were trained on food than cat, while more of cats were trained on yes. While yes now, more of dog, while yes, while more of cats were trained on affection than dog. Right?
Yes.
So, but at the end of the day, the final judgment is the one that incorporates all of them. So, because you look at, okay, the association between cat and dance and affection, those are the things. So the outcome variable, who is making noise? Because the outcome variable is whether they dance or not. So there you can say the exposures are the type of training and the animal. And we have already established the fact that more of the animal dance in response to, is it to food now or to affection to food? While cats dance more in response to food, and dog dance more in response to affection. And more of dog even dance more than cat. Those are the conclusion. So any you will see something, even though they call it log linear, they didn't take any logarithm here. Apart from the likelihood ratio chi-square, that it just has a logic for calculating likelihood. By the time we talk about Poisson regression, it's actually log. We're going to see how you calculate log. We take logarithm, just like the way we did for logistic regression. You take logarithm. In the equation, logarithm comes into it. Very well, you take logarithm. This one is just called, some people call it misnomer because they just say called log linear. At the end of the day, it's just your logic. It's not as if you are taking, you take any of the, yeah, you didn't take any logarithm of any of those things. So I don't know if there's any question. So if there's no question, before our time run out, we can just try to look at gleans at introduction to the Poisson regression, because that will be the talk of time till we finish this training. And I'm sure that's where people are interested in. That's what people are interested in. There's log linear because a special form of Poisson regression is log linear also. But in that one, you take the logarithm. You take this one is just answering log linear. Is a misnomer. Any question or comment? Dr. Low,
we are fine. We are fine.
Okay. If that's the case, let's just start discussion maybe for a few minutes and stop on the Poisson regression. If you don't have questions. Is somebody talking?
Okay. Hello, Doctor. Hello, Dr. Bura. Good evening.
Okay. Good evening. Good evening.
Yes, I have a question. Yes, please. Can you go back to the output table where you have estimates, Z test report, and then the confidence
interval? Okay. Sorry. Okay, this one.
Okay, yes. So in this analysis now, if you are reporting this, haven't written a paper, and you're reporting this as your result, what are the what will I call it now? Okay, what are the columns you need to which of these columns do you need to present? Because you're not going to present all this. Which are the important you need to present, and then how do you interpret it?
Yes, if it were to be paper now, number one, that cross tabulation that shows their percentage together will present that. Then the statistic you present, you may decide to choose the what do I call it? This one, the chi-square, or the t or the z to show. If you look at it now, any of these one shows all the level of interaction, both main effect, interaction effect, right? But the beauty of this one, of the Z one, is that it put everything in a table. Both the highest level interaction, animal, training, and dance. Can you see now? He put it here, animal and training, animal and dance, training and dance, animal, training and dance. So I think the Z, this to me, I'm more comfortable with this Z because it presents everything. If you are to present this one, you may have to now go and add this one, only this one to it. You know, why they didn't do is that if you want to present the chi-squares home, what you need to do is to come and add this K-way effect of the highest level, 20.305, and now add it to this table. But to be sincere with you, people maybe have to look at But to me, the Z in a more high impact journal, the Z give more information because it's able to give you confidence interval. I know that there's
Yes,
some
yeah.
there's some journal that will not even don't want to take p-value from you. If that's the case, you present this one with confidence interval, and you can even decide to remove the Z, because what you are seeing now is combination of hypothesis testing and confidence interval, more like repetition. Because without the significant p-value, you can interpret this confidence interval of the Z. You get it now?
Okay.
So,
And then, yes, and some people will want you to present the odds ratio. Where is the odds ratio in this table?
no, this one is not this one is the logic behind this one is not odd ratio. Is where we are talking of logistic regression. That's why you talk about odd ratio. If you do logistic regression or you just do calculate odd ratio from the table, this one is log linear. The odd ratio does not come in here. This one we already said that is like extension of chi-square. Yes, I mean it's like chi-square. So why Z can come in is that chi-square and Z, they are related. If you square Z, it gives you chi-square. Yes, I mean
Okay.
if you square,
Sorry,
that is actually the origin of chi-square. You square Z, distribution will give you chi-square. And because yes, because the Z give you the negative side and the positive side. You know in Z distribution, the mean is 0. So to the other side, But once you square it, it change to chi-square. You have removed the chi-square is always positive. It cannot be negative. So you understand me now. So this one give more because this one is able to give you the confidence interval. It give more for people that want to be thinking that line. It be more presentable. Yes, and that is why you may read some journal. Some people may not understand. Imagine that somebody brought categorical variable and what you see is Z and the confidence interval. For people that will not understand, they will not understand. In fact, you can present in some journal, the reviewer may tell you that they don't understand what you have done. You have not used the appropriate, you have not done the appropriate thing. Not knowing that they are the one that don't know the appropriate thing. You examine, so that's just it. So
okay. One more question.
Yeah.
The parameters and their estimates. This interaction that we've talked about, okay, are they different from predictors?
Predictor. You see, I know we okay, it's because it came late. I don't know when did you join? I know that at the inception, when we started, you were not around. So because I discussed it at the inception, even though it borrows from linear regression, but the interpretation is different. You don't talk about beta. You don't talk about regression coefficient. You don't talk about maybe the way you talk about predictor in case of regression. You don't talk about it here. It's like extension of chi-square. Just like the way you look at chi-square, you want to see association between two categorical variables. You decide which one, of course, you decide, okay, which one is outcome, which one is exposure. Like in this case now, we say, okay, training will be exposure, outcome will be the dance. But the only difference between this one and chi-square, plain chi-square, is that you can bring in 3 variables, 4 variables at the same time, rather than chi-square that look at association between 2 variables, nominal variables. This one can incorporate many at the same time. So that is where it looks like regression. Yes, I'm not. But the interpretation and the logic is not like regression.
Okay.
And that is why you still have to use your table of the way you percentage. When they say association, is your percentage you go to use to say, okay, oh, you see more of a dog dance in response to affection than food. Then more of cat dance in response to food than affection. From the percentage in the tabulation. But this statistic is just to quantify that the association is statistically significant.
Okay. Okay. All right. Thank you very much.
You're welcome. Yeah. Okay. I think we. Thank you. So I don't know. Consensus. Should we just have a glance, or we should stop here? It's 8:29, or should we have a glance of maybe have some talk about Poisson regression? Like
let's stop here, sir.
Let's stop here.
Okay. Somebody
Let's
was.
stop here.
Okay.
Let's
Somebody
stop
asked.
here, sir.
Okay. No worries. Yeah, I want to read some question. Okay. Okay. I think it was a question that there were questions they sent before. So any other question? So don't worry. Tomorrow so is going to be more exciting. And why I decided the workshop is on Poisson regression. Why I decided to put in log linear. The log linear has been hanging somewhere. And when I saw that somehow related to Poisson, because there are some aspect of Poisson they call log linear. That's why, okay, opportunity. Let me bring it in just to explain to it exists somewhere. You know, sometimes many people, when you try to present something, okay, let me just hand it.
Thank you very much, sir.
You're welcome. Let me hand the recording so that